says you have 30.
Oh, it was 12 chats. Sorry. I didn't have my glasses on. I was going to say, man, 12 people, somebody had to have died, you know. Twitch stream starting. Twitch. He's got that caffeine. Yeah, that's true. Well, no, I have the caffeine thing. The neurologist says I could have Parkinson's. It was a lot of fun, man. You're one of those guys that you're trying to jog and it looks pretty bad. What did Richard Pryor say about somebody who's, you know, moving, they're old and then moving slowly? What did they say? You move like old people, something. He said something terrible about that. I hope that never gets said about me. All right, how's the chat going here? 30 is good, but not great. Can I get one more person? Just one. It's like a live stream, right? Trying to get money. Just another $1. Don't you hate that? People get subscribers and keep on telling you and then say, just give me money to be on, you know, be on YouTube. Support my channel. Gift subs. Never look a gift horse in the mouth. Does that have anything to do with it? Super chat. I hate it when somebody who's wealthy has a channel and they're trying to get you to contribute $5, $10, $20 and stuff. I mean, come on, man. Oh well.
Yeah, I mean, like if they're begging for it, like that's ridiculous. But
well, it's one thing to be if they're sort of begging, but then they also say like they're a millionaire, right?
Yeah.
They say, wait, what is this? This is like a conventional wisdom situation. Money transfers from the poor people to the wealthy people. You know, it's a one-way street. And that bothers me because that's been happening for 2,000 years. You know. So
yeah.
We know because we can read things that are old, and they say that's what's happening. Member-supported lectures. I was thinking of slot channels. Well, hey, let's get going, you guys. Mr. Rogers, is that you? No, I don't think I would qualify for that. I'd have to clean out my mouth once. I got bad language. He didn't have bad language, at least not when it's on the screen. Okay, so what were we doing last time? Let's just pick that up. And it was kind of complicated, right? So we were looking at, we had 8 athletes. And 8 athletes, and how many first round outcomes are possible? So you have 8 athletes. So we were looking at this, okay? And it was a little bit complicated. So remember, think about this. The athletes are all distinct, and the venues to start out are all distinct. So let's say that these are our venues. Let's say they're tennis players, okay? So these are the venues, venue 1, 2, 3, and 4. And here we've got your 8 players. And the question is, how many different first round outcomes are possible? That would depend on how you started them, right? How you had assigned the players. Is everybody getting this? Is it recalling that we were talking about something like this at the end of last lecture? So what was the trick to doing this? Well, let me use a different color here. It's a horse of a different color. So how many ways could you assign these distinct athletes to these distinct venues? How many ways could we do that? What was that formula?
It's 8 choose 2, 2, 2, 2.
Right, and this is a very wonderful compact notation, and it also is easy to evaluate. Okay, so what is that exactly? What was the formula for this? This is 8 factorial over what?
2 factorial times 2 factorial.
Very good, very good. What's another name for that?
Yeah, 2 to the 4th.
Okay, so what? Is that the answer to the question? No, because we just, the tournament, it gets described as who played who, not where did they play. So we have to divide by something here. You know, it's 8 factorial, yeah, over the 2 to the 4th, but we don't distinguish if player A and player B play here, 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 here. So this would count all the ways where it matters where they played. So we have to divide by something to.
You have to divide by 4 factorial.
Very good, very good. I anticipate you're going to do well on the test.
Is divide, not multiply, right?
Yeah, it's divide. This
Oh, okay, yeah.
divide. However, we need to multiply by something. This is the interesting thing, because we're talking about the first round. There's going to be losers and winners, and how many different ways could we have in terms of losers and winners? Well, we've got all the different matches, but there's 4 matches going on, right? But how many outcomes are possible for each of those matches? It could be player A or player B, right? I mean, there's 2 for each one. Is everybody good with that? Right? So you have a match, right? One of the guys is going to win. But there's 2 possibilities for every match. So how many possibilities for all 4 matches? Well, okay.
2 to the 4th.
Yes. Right. Thank you. So what does this equal?
8 over 4 factorial. 8 factorial over 4 factorial.
Exactly. And this counts how many first round outcomes you could have, and outcome, it's decided by who played who also. It's not just, okay, it's already matched up. What are the outcomes? No, this is assigning all the players. And when I say assign, it's like who plays who, okay? And then also what could be the different possible result. This is a very large number, actually. I don't know what it is, but I don't know if I have it anymore. It's 1680.
6 times 5.
It's I don't want to take 2. This is a very surprisingly large number. You got 8 players, 8 tennis players. There's a lot of ways they could be matched up. It's surprising, right? And then it's surprising how many different outcomes are possible. Now, we know in real life that your best player, if he or she's playing in there, she's going to win. So that the chance of her losing is really low. But here we're just counting the total number of possibilities. You understand me, right? Not what's most likely, just the total number of possibilities. And why do we do this problem? Because it illustrates the multinomial coefficient. The hardest part is remembering this 4 factorial, okay? Because it doesn't matter, like player A and player B could play in that venue or they could play in this one. We don't distinguish between those possibilities. All we remember is who played who. Assume these venues the courts are the same. You know what I mean? It doesn't really matter which court they're playing on.
Professor?
Yes.
What did you say? Sorry, I missed that part where you said you multiply by 2 to the 4.
Oh, this one right here?
Yes.
These are the outcomes. So these are the results of the matches. Who's going to, how many different ways could we have winners and losers? So
okay. Thank you.
It really is. Each match has 2 possibilities. Player A won or player B won. There's no ties. I'm not sure. In tennis, there's no ties, right? In pro football, there's ties. In hockey, that's an excellent. It depends on whether it's regular season or postseason in hockey, I think. If it's regular season, they go to shutout, right? But I used to be a hockey fan. I forgot now. But in postseason, I think you can have 7 overtimes or something crazy like that. I've got how many people here? 32 people. Somebody probably is a hockey fan, a Kings fan or a Ducks fan. They say, "How do you not know this guy if you're a fan?" But I don't remember. I remember there was one game that went to 7 overtimes and nobody could believe it. It's just like, I'll be the record. Okay, are we good with this? We're on the next topic. Somebody says from Brandon, is the exam next week? Hopefully I will get it out. Yes, I should. If I'm doing my job, I should post up this test, and in the groups, if you have groups, you can work on it. Between groups, I don't want communication. I don't want one group doing, posting up, hey, for everybody, being anonymous or whatever you want to call it. I don't want that. The groups are big, but I don't want them sharing information.
Good question, Professor.
Yeah.
When how can we add up to a group? Because I remember I joined late, so like I can't. I don't know.
Post up on the discussion board, for the class, whatever. And you could say something about yourself, like you you took these math classes, you did well. You can sort of advertise yourself to get, because each group has a maximum size of 8. So there's probably a group with 3 people that could use another person.
Professor?
Okay.
Yeah.
Are we allowed to group up with people from other classes, or does it have to be the one that you're
It has to be from this class, because you see, when I do
Okay.
the grades, I have to go, you know what I mean?
Yeah.
It's just, I wish that we would have a super, I wish this was really online, because we would just have one class, But
Yeah.
the truth of the matter is, you probably find this kind of crazy. This is not an online class. You probably don't know that. It's not online. It's distance learning, but it's not online. Online means you work when you want. You can, you have a lot more freedom to do what they wouldn't. I guess there's this general feeling in our leadership, in our department, that online is ineffective for most students. So we have to, it forces us to meet at these hours and do things like, whatever. It's just, I don't want to get into the argument. I'm not high enough to have any influence on that. But it's to think this is online. It's not true. You don't have the freedoms you would have if it was an online course.
Yeah, I'm just from the 5 o'clock class, and this is just, I like getting in here earlier and just having more of my day. So.
Good. I'm the same way. I mean, I don't learn. First of all, I learn slowly anyhow. And if I leave it till 5 p.m. to learn something new, it ain't happening. Okay, somebody said something. So who in here has space for one more? Depends. Are you a math major, CS? Give some kind of. Don't just say, "Here I am, do my work for me." Like, what's your GPA? I mean, you try to make a case for it, because nobody wants to get stuck with, with a drafter, I mean, I know you're not. I'm not saying you are. I'm just saying it's always good when you're looking for time in a group. Give some background, The best thing you can say is you're already in the industry, already working, and people will say, "Yeah, maybe somebody who can get me an internship or something like that." It's happened before. It's happened. Okay, I'm going to erase this and go on to the next topic. I'm trying to give some problems that might be similar to what's be on the test here. So the next thing involves it's a problem that goes like this. It's in our book. It's the last one. What number is it? Number 34, page 17, number 34. This is the so-called fish problem. And it's a little tricky. You can get fooled by this. So you catch 10 fish, and there's 5 species, and 5 varieties of fish. And the question is, how many different outcomes are possible here? Now, outcomes means like, okay, I got, one of 4 types and then 6 of another, something like that. Okay, so it's not like when you say outcomes, it's not like among a single species you talk about you differentiate. No, you just got like 5 trout or something like that. So how many outcomes are possible, and how do we approach it? Does anybody want to suggest something? How do we approach this problem? How many outcomes?
Well, it'd be helpful to recognize that this is like finding integer solutions to n1 through n5 equals 10.
Very good. And just my curiosity, did you see this in the book before, or you just got it? You came up with it right now?
We've done this problem, I think, like 4 times in different ways.
Okay, so that's how. So you didn't actually hunt this problem down and do it in the book.
No.
Okay, good. Okay, that's good. Well, that's good that you recognize it. You're right. So what would that look like? So you would have what? N1. These are the different species, the number of each species, right? And it has to equal what?
10.
And we're not saying that you have to have one of each, okay? That would be unlikely if you're fishing anyhow, right? If you get all of them represented. Some of the fish are probably harder to catch than others. But what would be the answer to that?
Well, we have a formula.
We have a formula. That formulas are good for excusing us from thinking. We just follow the formula. And that's essentially, that's just the way it is. So what is it? What was that formula?
N plus r minus 1, choose r minus 1.
Right, so in this case, what does that evaluate to? 10 plus what?
10 plus 5 minus 1.
Oh, plus 5, yeah, okay, so 10 plus, let's just cheat a little bit here. Ah! Oh my gosh. I had too much fun in the previous hour. So this is 14 choose 4, which is a weird number. So he's playing, Ross plays some game with numbers. It's just funny, because he's done so many additions. He fools with the numbers to make it something. So what do you think the answer? What would be a weird number? Let me give you a hint. 2001 is Space Odyssey. Okay, somebody's probably calculating this, but somebody can just, what does the hint say? So 2001 is Space Odyssey. So what would be a weird
I haven't
number?
seen that movie.
Oh no, I'm just referring to the number 2001. So it's probably what?
9,000? Oh. God.
He plays these games in there. I mean, who would know what 14 choose 4 was? I assume that's correct.
I just did it by hand. It's 210.
Uh-huh.
That's 10 times 3 times 7 after you do all the cancellation.
Let's check it out. What do you think it was? I'm just
210.
210. Huh, maybe I calculated wrong. I'm thinking of a different problem. So 14 times 13 times 12.
Oh, I see what I did wrong. It's 14, not 10.
Oh.
But this number will stick in your mind. I don't know. He does this throughout the book. It's just weird. It's a little game he plays with the readers. Okay, good. Now that was a total review. But then this problem has a star, and a star usually means watch out. It's going to step up the game a little bit. And I've forgotten what the side condition is. I think the next condition is exactly 2. Let me check real quick and look. 3. So how many outcomes and this is a side condition, if exactly 3 are trout. So he's just up the game a little bit here, okay? Now this, we don't really have a formula for this, right? He's saying exactly 3 are trout. How do we adjust this template that we have to accommodate this situation?
Well, this is almost like saying that N1 equals 3 and kind of
So that
adjusting.
effectively, if it's exactly 3, then that's basically like you have 1 less bucket and 3 less fish. So basically,
Right.
N and
Right.
R are now smaller.
Right. And so what is the takeaway from this? Don't fish from the pier. Do not eat what you catch from the pier. No. I always tell people that, and they don't listen to me. They say, "Oh, it's fresh, man. It's fresh." Yeah, it's fresh and radioactive or something.
Yeah, I think basically this means like when something is fixed, it's effectively like it's not there because we don't have to think about it.
Yes, that's a way to look at it, right? That's the way to look at it. If you have exactly 3, but I have to. So how do I set this? I mean, what do we need to do though to be on the safe side? Okay, not eat. What is the name of that fish you can catch on the pier? I mean, people say what's in a name, but does anybody know? One of the most common fish that's caught there? It's called white croaker. And I don't know, man, but if you eat that, what's in the name? And he's thinking, I'm eating croaker. What's going to happen to me?
That's ominous.
Sorry, you guys are probably going to get fired for saying it. But anyhow, so let's see. So this would be 7 then, right?
Yeah.
Now, as you were saying, how many variables do we have? Now it's the formula people can come in. It's the formula. Okay, now we can apply the formula. So the formula says what? 7 plus, what's R minus 1?
3.
1, 2, 3, 4, 3. Choose 3. Now let's see how fast we can calculate this. 10, choose 3. What is that? Are we good on it? Did I lose anybody on the 10? Yeah, I lost a couple. It was that white croaker remark. I'm sorry, you guys. I don't know. Would you eat it? Somebody said, it's fresh. We just took it off the pier, man. Okay, what's 10, choose 3? Now, okay. How fast are you guys doing this?
And
Can we do it in our head? Remember, this is a raw problem, so maybe there's a way to quickly get it.
yeah, you could just say 10 times 3 times 4, if I'm doing that right.
Well, it's 10 times 9 times 8, right?
Yeah, and then divided by 3 factorial. So I just kind of canceled out a few terms common. Yeah.
So it's 120.
So yeah, 120.
This is weird. The previous one wasn't okay, whatever. I thought I saw 120 earlier. Yeah, go ahead.
What happened to the M1?
It is 3, because the assumption is, let's say that's the species that is trout.
Oh, okay. So we already know M1, so we can put a number in place.
Yeah, right.
Okay.
Right.
Yeah.
Right. It's a star problem, so it's not trivial. You know what I mean? When I first did this, I couldn't get it right. It was not easy for me when I first did this, because I'm used to just following the formula: plug in, plug and chug, plug and chug, plug and chug, plug and chug. I missed that kind of approach, and I was caught off guard on the next one. But are we good with this one?
Yeah.
So how could we change this to make it harder? In math, it happens so often in word problems. They don't have exactly, but they use what? They use the term. They use the phrase "at least," at least.
Mm-hmm.
And I don't know about your mind, but in my mind, when I see "at least," I focus on the least, and I'm looking for something small. But "at least" means that or larger. It doesn't mean small. I don't know, just the way I was taught. With the language, it's confusing. But if we put "at least," if I write that wicked phrase. And this is a little tricky, you guys. Think about it. At least 3 are trout. We can't do like we did before, right? We can't go like we went. We've got to do something different here. We're going to have to do something different. And what's going to have to be different?
Shift the numbers around. We could say that we could treat it again like the same kind of problem so that we can use the formula again, but we'd have to.
Yes.
We still have the same number of buckets, but 3 less fish, I think. And then we kind of add on a number. I don't know.
You have the right idea. You have the right idea, and you have the right idea. But this is a case where, believe it or not, we need to change variable.
Mm-hmm.
So right now you've got N1, right? So if we can write this if we can look at this as N1 minus 3.
Oh, yeah, there you go.
Now, if that variable is 0, that means we have 3.
Cool.
So this is the new N1, and it doesn't help. It doesn't help to rewrite it. This is so, but the fact is, we did put a minus 3. So what has to happen to this? You want it to be and you're right about the fact that 3 fish have already been taken, right? 3 trout. So that, to me, that means that distributed here, you have less fish. So how much less fish?
3 less fish.
Does that make sense? Let's stop there, because this is the absolute crux of the star problem in Ross. This is kind of like the crowning achievement of chapter 1.
Wow.
So does that make sense? Because now I've got these categories, right? And you're handicapping this like this. So this assumption is you already have 3 trout in the bag, in your possession. So that means that there's 7 now at stake, and it could be more trout. This variable could be a 1 or a 2. This new variable. If it was a 2, you would have 5 trout, right? So every possibility now is still in play as long, under the constraint that you've got 3 trout already in the bucket.
My mind just was like blown. I
Well,
get it now. That's
That's
cool.
the problem with combinatorics. We're counting things, right? It's so easy. And when I first did this, I wasn't sure. I kept making a stupid mistake. I left this as a 10 instead of a 7.
Yeah, I didn't see that at first. I was like, I thought it was gonna I was gonna do the other thing. I was gonna make it 13, but I was like, no, that's wrong.
Well, maybe would it help? How many buckets?
That would make it more.
This, in case there's somebody that doesn't understand it, how can we make this clear? So there's already 3 trout, and we want to know basically how many ways we could put 7 fish into these buckets here, right? That's really that's the problem. So you have 7 fish, and they could go anywhere here, and we know how to count that.
Yeah, so just dump the bucket and be like, okay, they're already accounted for.
Yeah. You could or you could leave them in there. I mean, if you get this, that means that now you've got 1 more trout.
Put a false bottom in it.
Okay, but I want to make sure everybody. I know you got it, but I want to make sure that we don't lose any more people. I notice whenever I do a stupid joke, I lose a person. I guess I offend somebody, but it's going to get worse, you guys. I don't know. I spent too much time on the internet. I just. World Star, too much time. When I want to go to sleep, I watch a little of that and it puts me to sleep. Okay. So we did this. Let's go on to the next. Oh, we didn't get the answer. What's the answer?
No idea.
What's the answer to this? What's the answer? So it's n plus what? How many variables?
Okay, 7 plus 4 again, I think. Yeah, choose 4.
Well, now it's 11. Choose 4. I don't know what that's supposed to be. Oh. Wait a second. Did I do this right? I have 5, so it's supposed to. Wait a second.
Well, it's 7 plus 5 minus 1.
This is weird because I have. Oh, I did a different. Okay, you know what? I did this with 2 here, so that's why it's something different. So I'm not doing the correct problem. I should have in the book. It says, I'm sorry to be scatterbrained here. At least 2 are trout. So in that case, what happens here? So just modify it. What do we put?
-2.
And then I have to do what over here?
Add 1, so that it's -2 from 10, so 8.
So what's the answer? So 8 plus what?
4.
Plus 4. Choose
4.
So this is no wonder I got the different answer.
Okay.
So I'm sorry, I made up my own. So 12 choose 4 is 495. That's what I get. I don't have an answer sheet, but I taught this last semester, so I think I remember that's probably the correct answer. I hope that's the problem in the book.
12 factorial over 8 factorial over 4 factorial.
I think at this point you're better off just using the calculator to do it. All right. Okay. So let's do one more problem here from the book. I'm kind of wrapping up chapter 1 here. Are you guys good with this so far? I think so, right? That's the feeling I'm getting. So there's a problem that involves lefts and rights, and there's an old joke about. I can't say it. Okay, so lefts and rights, or rights and lefts. You have a grid. It's a 4x5 grid. This is an easier problem, so I'm trying to pick up people that are struggling at this moment. Okay. I'm trying to pick up the stragglers. So we have so 4 up and 5 over. 1, 2, 3, 4, 5. We have a grid like this, and I'm doing my best to make this legible. Okay, so you want to start here, and you want to end here. And if you're a math person, you'll understand when I say I'm looking for simple paths from this lower left-hand corner to the upper right. Simple path. What's a simple path, you guys? If you're not a math major, do you know what a simple path is? I mean, it's simple, but what's the term mean?
The shortest path to get to your destination.
Well, it turns out it usually is the show, but a simple path is what? Because you can go right or you can go up. So right, or call that left, or right or up, across or up.
Maybe the fewest number of line segments or turns.
Well, okay. When somebody says, this is important for at least if you take computer science, when somebody says a simple path through the graph, it means that you don't revisit any of the nodes or vertices that you already did. Okay.
Mm-hmm.
So I couldn't go back and forth. The idea is, how many simple paths are there from here to here? Count them. So let's just put one. Let me use a very rare color for me. Let's do one of them. So I could go right, up, right, up, right, and up. That's one of them, right? What is that stupid joke about lefts and rights?
About the what?
Lefts, rights, and lefts. So I won't go. You guys can look it up for your own edification. But anyhow, so how many paths are there? Can you think of another? What's another way you could go through here?
Zigzag all the way through every row.
Right, like it's like a staircase. But I've kind of made a staircase here.
Or not every row.
You could have gone.
You can go straight up, then straight right.
Yeah, you could have gone straight up, and then straight. Yeah, that's another way to do it. How do we count it? This is an excellent problem if you're just getting started. You have some latency in picking up the concepts. What's the first thing we have to notice about this? No matter what you do, if you're going from here to here, what's the thing that no matter what, all these paths have something in common? All these possible paths. What is that?
There's a maximum number of steps. I honestly, I've never seen this problem before. I don't know how to do it.
Good. This is good. I mean, it's good because it's a learning. You know what I mean? It's something we can get something out of.
I'm still not sure I understand what a simple path means. So
you can't revisit. You can't go boom, 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 boom. You can't hit one of those
cycles.
Right. You can't go back to just how many paths to get from. But Aim, could I ask you?
Could zigzag.
Yeah.
No, but like if you went like you could go like all the way to the right, then up, and then all the way to the left, and then up, and then
you're done now.
Back towards where you're
so
supposed to go.
We mean like this. No, okay.
You could like backtrack as long as you don't visit a node, right?
You can only make. Okay, I'm sorry, I was unclear about the problem. You can only make rights, equal lefts and equal rights. You can only make rights. Only make what? Or
ups.
Right. No ups, no downs, no balloon payments. So only make rights or ups.
Okay.
Sorry,
so,
I wasn't clear about that.
So that's simpler.
Yeah. I'm sorry about that. Aim, was that the thing that was confusing you? Can I ask you?
Hold on. Wait, why can't we go up?
You can go rights or ups.
Okay, so not left.
Not left or down.
And not down.
Okay. Then let you write that down.
That was my fault for not making that clear.
You're better than most textbooks, so don't worry.
I don't think so. Not Ross. Ross is something else.
Mm-hmm.
I once wrote him. I had a question about something in probability, and he's such a big. He didn't respond, and it's like he's such a big shot that he just shines off. You'd have to be like a well-known professor to get a response out of him. He just said, "Shut up," equal rights and equal lefts, or whatever he said. Okay, so okay. Let me go back to. Sorry for my lack of preparation. We'll go back, and so what do all of these paths have in common?
They all have 7 steps. Sorry,
Yeah,
go ahead.
Okay, sorry, man, I couldn't hear it. They all have what?
I'll let someone else talk.
Okay, how many rights does every path have?
Are there 3 or 4?
Well, let's see.
I believe they have It has the same number each time of rights.
Right. So like I mean, look at this one. 1, 2, 3. Sorry.
Yeah,
One,
you're right.
2, 3. What's wrong with me? 1, 2, 3, 4. It's got 4 rights and how many ups?
3.
So how many steps? Each one is going to have how many steps?
7.
You're going to notice that I love to write vectors. Okay. So now we're getting someplace. So we know they all have this
Excellent.
7 steps, but they all have to have how many rights?
4 rights.
Right. And how many ups?
3.
And no downs, or no ups, no downs, no balloon payments. It's going to be this or this. So I should have 7 slots. So now can I stop here and let me go back to AIM. So now can you solve the problem?
Oh yeah, that's just a multinomial because we know how many steps total and we know how many of each kind. So it's 7 choose 4, 3.
You lost me.
She's right. She's actually used a formula. I wasn't expecting that. Because what I was looking at is I would look at my ups, right? I mean, it's the same answer as she's saying, but I was going to do it more primitive, in a more primitive way. So I have how many? 7 slots, right? So of those 7 slots, I know that 3 have to be ups. So is that good? So 3 of them are going to be up. So how many ways could I choose those ups?
Yeah. So between those, any given arrangement like that, 3 factorial.
It's 7 choose 3, and they might say, "Well, wait, where are the rights going to go?" Well, they don't got no choice. The rights. The rights that's what was left, so there's really no choice with that.
Oh.
So the answer, I think, is 7 choose 3. Now let me check.
Well, yeah, it's the same thing. You don't need to use a multinomial for 2. That's just the way my brain thought of it.
No, but I like that because you're using the formula. I like it.
I don't like multinomials.
Let's check the formula. Okay, let's check it. So there were 7. There were how to do this. So you had how many 7 altogether, right? And they could be distributed into the 3 ups or the 4 downs, right? Or 4 rights. I believe this is the formula she was looking at.
Yes.
So what is this equal to? 7 factorial, the 3 factorial times 4 factorial. Right, now how the hell is that 7 choose 3? Well, if you look carefully at that, if you look at it,
oh, it is, isn't it?
it really is 7 choose 3. It's exactly the same answer, but it's more, I like it better because we're making use of stuff we already did.
Yeah. Well, the way I think of it is like probably I was thinking the same thing as that formula on the left, but it's just I think of it in terms of the primitive parts of like how many ways can we arrange everything, and then how many how many ways can we arrange all the duplicates. So I'm like,
that was similar to Pepper, right, or something like that. That kind of problem.
What's that?
Remember the Pepper problem? How many words, distinct words, can you make out of the letters in Pepper?
Yeah, I'm thinking of it that way.
It's similar, but
so we have 2 ways of permutations of 7, and then the U's are all the same, so we do permutations of U's and ups, and then permutations of rights to get rid of the duplicates.
Yes. Okay, so how can we jazz this up just a little bit? This is for computer people, okay? I've got math people in the class, and you probably don't understand why I would do something dumb like this. But for computer people, there's a principle called divide and conquer, DNC. Okay? What's that stand for? Democratic National Committee? No, divide and conquer, DNC. So a question could be asked, how many paths of that type could you find that go through Mr. Green here? I'll just call him Greenie. So how many I'm sorry, you guys. I got to stay sane now doing this because I've got 2 more after this to deal with. So how is this a divide and conquer a problem?
Because there's only 3 choices, right?
Well, remember, you can only make rights or ups. There's no lefts in this problem.
Yeah.
So it's not a fighting thing. So it's only make rights or ups. So if we have the additional condition, then you've got to go through here.
You
You
would have to
could-
find the ways from going from blue to green first, and then from green to red, and put those together.
Exactly.
Yeah.
Exactly. So you actually have you're splitting the problem into two subproblems, right? This is a basic thing. So you have a subproblem involving this grid, and then you have a subproblem involving the other grid. So you could go up here. So you could actually, you have this grid right here. So you definitely, from this point, you could go up, right? So how many, let's say this. What would be the answer then? Yeah, okay, well, this is a subproblem. From this to this, and from this to this. What was the answer down here? So let's see if we remember. Huh? So how many rights and how many lefts? One, two. So this is 4 total, right? So how many rights do you have? 4 choose 2. You have four moves made. 1, 2, 3, 4. 1, 2, 3.
Yeah.
4. So I believe it's 4 choose 2 who handle this.
Yeah,
I could be wrong because I didn't prepare this. And then what's the other one here?
That one's really small. It's
1, 2, 3. You have 3, and how many?
3 choose 1 or 3 choose 2.
Right. What's this equal to?
That's 3 times. I believe 3 choose 1 ends up being 3, and
Right.
4 choose 2 is like. I thought that was. Wait. Oh. 6?
Well, 6 times 3.
Okay.
So
I was still hung up on doing. The math.
yeah, 4 choose 2 is 6.
Yeah, I think it's at least it's happened for me, and I do research in discrete math these days, or I try to do it, and it's good to remember some of these lower binomial coefficients because they come up so frequently in the book. So and of course, having said that, I'll blow one in the course of of teaching. But I mean, maybe we should know like 5 choose 2, 5 choose 3. Those are the same, and I think they're 10, and then 6 choose 3.
I'd rather just be really good at computing it, like quickly.
Well, there's nothing quicker than
I like
already
being able
knowing
to just
already
understand.
knowing that. You know what I mean?
Yeah, I know. I'll just. It'll come naturally. The memorization will come over time after I've practiced.
Well, I wish I could say the same because it did not happen for me. I had to like consciously try to remember that 4 choose 2.
Yeah, I would prefer, just in general, I'd rather understand some things and remember it.
Chapter 2. Okay, guys, there's an issue here. We're supposed to talk about probability, and if we were taking an advanced class, they would start the whole thing with a probability measure or some thing like that, and measurable subsets and all this stuff. But really, the better thing to do is to show a need for establishing the axioms of probability and why it has to be done in a certain way. If you don't set things up correctly, you can get into paradoxes and arguments about what something is or isn't. And let me give you a problem, okay? This appeared in some supplement to the LA Times. It's called Parade Magazine. I don't know, it's buried in there somewhere, or used to be. And the name of the person who wrote the problem, or had the column, that wrote several problems, is Marilyn Vos Savant. It's an interesting name, right? If your last name is Savant. Do you think this person, what do you think this person, what special quality do you think this person might have with the last name is Savant? Just let me pick on somebody. let me pick. I don't want to. I wouldn't embarrass. Would I embarrass somebody like that? She has apparently she's got the highest IQ on record. Took a test and got the highest. So,
Oh.
world's smartest person as measured by IQ, Marilyn Boltzmann. So she came up with this problem, a very simple problem, and I hope I can convey it to you, okay? Because the thing is, if I was like any other stupid teacher, I would just write down, this is a sample space, this is an example. The thing is, this is not the way the human mind functions, in my opinion. It's not the way. My opinion is you give somebody a problem, they can't solve it, they need a tool, then you bring it on and say, this is the thing you're missing to complete the job. I'm just dumbfounded by the way math gets taught. They usually go theorem, proof, example. It should be example first, cannot do it. Now you need some mathematical insight. You need your theorem,
Yeah.
right? And then you prove it to make sure, later on, after you've done enough cases where you believe it, our minds are not accepting. The mind is very discerning, discriminating. And if somebody says, here's a theorem, prove it, your mind doesn't want to do it. Why? Because it doesn't know, it's not confident, you haven't done enough examples that thing is true. And believe me, there's nothing more frustrating in this world than if you're a mathematician and you're trying to prove something that isn't true. Because that process will take forever. Okay, so let's just, and I hope to God I can get this correct. So there's two people here, unrelated, and the man says he has two kids, and the eldest is a boy. That's what he reports. So he's asked about his. He said he has two kids, and his eldest is a boy. Now, a woman is also asked about her kids. She says the same thing. She's got two kids, and at least there's that phrase that causes a lot of trouble, right? I mean, come on, you guys. Is there anybody that's going to be a high school, secondary math teacher in this class? How many people do I got? 32? Anybody? Anybody interested in K through 12 teaching?
I think a lot of people here are actually. This is a class that people can take for the math for teaching major.
Thank you for saying that. But sometimes we say that, but then it turns out there's nobody, and I felt like, but I'm.
Oh well, okay. Well, I am.
That's excellent. That's excellent. So this at least causes trouble. Whenever that pops up, that's going to cause trouble. So this is when you're teaching, like word problems, even in middle school, you've got to be careful about using that phrase. At least one is a boy. I hope you can read my handwriting. There's two scenarios here, okay? And I know I'm writing kind of small. Well, let's just review what the first one says. The person's asked about their kids, and he says, my eldest is a boy. I've got two kids, my eldest is a boy. The older one is a boy. Another person, unrelated, is asked, I've got two, about your kids. You got two kids, she says, and at least one is a boy. So what's the issue here? What is the probability? We know in this case what probability is. I'm not going to write it out. Just prob in this class means probably or probability. What's the probability that both kids are boys? Okay, just get used to my shorthand. Now that I'm working on a compressed blackboard, I have to do shorthand. What is the probability that both kids are boys? Now, there's two situations here. So let me ask you, what would be the answer in this case? What's the answer?
Oh, never mind.
Or just guess. I want you to guess. I don't want you to show me your power.
I didn't realize, there's two kids. I was going to be like, how many kids are there?
Yeah. But think about it. My eldest, what's the first thing that comes to mind? What's the first thing that comes to mind? Just read that quickly and what would pop into your mind? Okay, the older one's a boy. We didn't say nothing about the younger one, so what?
What pops into my head is, I don't know, 50-50?
Yes, that's what popped into my head. Let me ask, how about aim? What if you saw this lingo here, what would you, in both cases, what might you suspect is?
Well, hold on. I'm doing the second one. I'm still writing it out. But yeah, the first one, we're already saying the first one's a boy. So the only thing that we need is the second one.
Do you guys? Well, she's calculating. Do you guys?
I got it.
Oh, you got it.
Sorry.
Okay.
Yeah. The other one is 1/3.
Okay. This problem, if people have not had, like you guys are all college, students, you're taking a junior level course, which is pretty hard. And so you're not so fooled by this, but a lot of people will say 50% for both. I'm telling you. And if you tell them that you're wrong, they will argue with you. They say, "What do you mean?" How do you convince somebody that these apparently, I haven't checked it because it's been a while since I looked at this. How do you convince somebody this is the correct those are the correct proportions or probability? P and probability and proportion start with P, so it can make either one. So
I don't know, because I'm not convinced.
Good. I'm glad to hear that, because she wrote this up in a column, and she also wrote up another problem which is very famous. It's the car and goats fiasco.
The Monty Hall problem.
And I'm glad you know that. It sounds like you've been either. I don't know where you would have learned that if you hadn't had this course. I'm surprised.
Actually, it's pretty popular. It showed up in a few TV shows, and being the math major friend, anybody who's seen that problem asks me about it.
Uh-huh.
It happens. So yeah, I've had to explain it a few hundred times.
Good. Well, there's a funny thing. It's a truth. I went to the Wikipedia, and it's when she subsequently gave the answer to it in her column. A lot of people complained that she was unqualified to state the answer, and her answer was not only was wrong, but she was unqualified to state it. And I remember there was one letter that she published a letter, but that she received and said something. If you are right, this country is in serious trouble. And this guy was high up in the federal government. He was in some sort of intelligence agency. and I think, I don't know if it was that guy.
Well, what was it that she said?
Oh, she solved this other puzzle called the car and goats puzzle. And we could do that later, but I don't want to take the time up. But I'm just saying that because she didn't have the credentials, like a college degree or a PhD or something like that, they just disavowed all of her conclusions.
Mm-hmm.
So she's famous for that. I bet that guy, he was in Army intelligence, I remember.
I've heard this story before, but I thought she was right.
She was right, but these guys were complaining.
Yeah.
She was wrong. And you know what? I have to be honest as a human being. I didn't understand that. It got me too, and somebody caught me on it. And I'll tell you that story if I have more time some other time. But I got caught on this too.
So do you want me to explain the other one, or do you want to?
No, we're going to do it. We'll do it right now.
Okay.
We're missing something. We're missing a tool. Does anybody know what that tool could be?
Any understanding of what's
That's a
going
script S.
That's what I missed.
Script S. S stands for what? In
Sample space?
Sample space, right. This is the set of all possible outcomes of the experiment. So let's take a look at this. So let's look at this case right here. So what are the outcomes possible? The person could have two boys. Wait a second. Let's just say before the additional information, okay? Before the additional information, boys and girls are equally likely, okay? The couple's equally likely to have a boy or girl. So what is the totality of possibilities of that before you add these additional side conditions? So how many possibilities? Are we good with this? And these are equally likely. Are we good with that? Before you add the side conditions, all you know is a person's got two kids. You might say, this is a problem, okay? Somebody could say, well, that's the same situation as this. They got one girl and one boy, and why am I writing that twice? Well, anybody that's had kids will know in the pediatrician's office that when you're doing records, that's the first record, this is the second. Your first child was a boy, the second was a girl.
Mm-hmm.
those are actually, they're all equally likely, but they're actually different situation. Okay.
Yeah.
So we ignore the possibility of twins?
How would that affect anything?
Well, even if they're twins, then
One still has to be eldest. Yeah. Never mind.
Yeah, no, technically, yeah. Unless it's cesarean section, I don't know how that works. I don't know. I know. I just remember Macbeth, right? Remember? He said a woman born. Aren't
You don't want that. You don't want to start calling people like they're the same. That's no.
Right. But at Macbeth, what was it? You don't have to worry about any man of woman born to that will kill you. Then at the end, what happens? Well, he gets killed by somebody who was delivered by cesarean section. So technically, in the old days, not born, right? Oh well. Okay, so let's look at these two possibilities. So if we're over here, these are all equally likely. So of these, how many correspond to this? So I already said eldest would be the first one, right? So which ones have the eldest? Which possibilities have the eldest as a boy? Right? So what do we, what's the probability of being, if all these are equally likely and we're just saying what's the chance of this happening, what is it? You're good with that, right?
Yeah.
Good, we're good to go. Now let's do the same thing over here, and something's going to be a little bit different. Boy, girl, something's going to be a little bit different here.
Oh shit.
Now, what did they say? At least one is a boy. Well, that's a little more likely. I mean, it corresponds to what?
What the fuck?
Okay, it corresponds to that. So wait a second now. At least I don't know if 1/3 is correct here. Aim, you can still retract your answer if you want. So.
Well, it's the number of ways that you can have the desired outcome, which is.
No, you're right.
Okay.
You're right. So this is our new sample space. You're right. Oh, sorry, I'm just tired. So this is the new sample space, right? So in other words, we know originally all these were equally likely. So if you're just restricting to these would still be equally likely. Each is 1/3, right? So you were right. Sorry, false alarm.
No worry.
Oh my god.
I mean, so you're saved by the you're saved by the bell. So these are equally likely. This is a situation now, okay? And in this situation, what's the chance that at least one is a boy? That both are boys. I erased it. That both are boys. Well, there's only one, right?
Yeah.
So of the.
Why is that true? It's been proven, and I still don't understand.
Well, okay. So when this is stated, this is your sample space.
Yeah.
Okay. And why do we assume it's equally likely? Because these originally, we know that globally,
Yes.
without the condition, those are equally likely. So these are now they inherit the equal likelihood. So we know that this is the sum total of all possibilities respecting these two conditions. So they're all equally likely. So if you said, what is the probability given that sample space, given at least one is a boy, of having both boys, it is correct. Aim is right. It's 1/3. Okay.
So there's some additional information in the whole eldest is a boy thing that I wasn't even paying attention to. I guess.
Yes. I don't know.
Right.
It's one of the,
Like
how would you say that? I mean, because the question is, yeah, go ahead.
Yeah, no, that's exactly it. There is extra information in the eldest being a boy. You know which, like you get to eliminate the one where the youngest is a boy. And honestly, when I'm explaining this to like the students that I tutor, my go-to thing is probability is not intuitive. Sometimes you really do just have to write it down.
Yes.
That is so weird.
Yes. In other words, you're trying to tell me that it's not intuitive, right? Is that what you're saying? That sometimes you have to.
It's really not. And like it's like what you were saying in the first lecture of this is why people gamble their money away. So whenever you said that, I'm like, yeah, really, that's why we have statistics and probability in K through 12.
You're very positive thinking. I wonder if this probability theory that they learn will lead them not to gamble. But I am afraid that.
I mean, I hope so. I mean, that's kind of my hope is explaining this kind of thing and showing problems where like how the house always wins. And, that's kind of like my hope in teaching probability and statistics sections.
Nice.
Well, I always try to tell, this is stupid, but, I being old, I hang with lots of different people in the course of my life. And they tell me, some people tell me that they went to Pachinga or whatever it is, when they call it. And I tell them, do not go, or some people, they say, don't go Indian. Why is that? Because the odds are, they can change the odds on the slot machines, and they don't have competition like they have in Las Vegas. So in other words, you can't walk across the street to a different casino. So the so-called payback is a lot worse. And people probably think I'm crazy. And who goes Indian? We don't know anybody. Well, apparently, a lot of people do, because those casinos do really well. I mean, especially even in the pandemic,
Wow.
Okay, so let's. I'm sorry, I kind of got this up a little bit, but I hope you guys got the thing I wanted you to take away is that we have to write the sample space down. If I don't write the sample space, I don't think I'd succeed at convincing anybody about this.
It's still so weird saying at least one is a boy means that the second one being a boy is even less likely than saying that the eldest is a boy. I just find that interesting.
Well, I think, like Ames says, you just have to. That's one of the things, with conditional. This is an example of conditional probability. I think what she's saying is sometimes you just have to go with the formulas and you just chunk it out, because you get into problems like this where it's not. It's just. It's hard to get a good grasp of something that in your own brain is saying, no, it's the same. It sounds the same. In English, it sounds the same, right? That's the problem.
I feel like, to me, I just, like, it's a case of extracting all of the information. Like, I was only thinking of it in terms of, one of them's a boy, but there's more to it than that.
This kind of thinking actually pervades legal things like contracts and stuff. And I'm sure lawyers are very attuned to the exact meaning of the words or the phrases they're using, because if it turns out they haven't taken into account something that can happen, then their client could lose a lot of money. It's something to do with a real estate deal or something. So, yeah, I think there's value in looking at these things. Okay, let's just do some quickies, okay, just to wind down. So sample space examples. You race 5 horses, no ties. And so how many what do they call that? Post? Sorry, what do they call that? Post finish? I'm sorry,
Places?
post something. What do they say when?
Podium?
No, post. It's when they raced and now that's the order that they're in. How many post orders? Is that what it is?
I don't know what they call it, but
you guys don't go to Santa Anita and place bets? No.
I've been there.
So how many?
No, we're math majors. We know better.
I've made like a couple of like $2 bets.
Yeah, but I feel like I'm being really ignorant here, not knowing common language. But you race 5 horses, so the sample space will be all the outcomes. So how many outcomes are there? Well, here are your horses, C, D, E. So how many finishes? We know this way. This is pretty easy. But how many orders are possible? How many finished posted?
5 factorial.
Right, 120. Right. So your sample space is 120 for this case. We use those bars to represent the cardinality of this. Those are all the possible outcomes. How about, let me check the time here. How about rolling 2 dice? Yeah, so how about tossing 2 dice? So what's the sample space look like for that?
6 times 6.
Right. Now, you have to be careful about I've actually had experts tell me, if you just like toss a coin, you toss two coins. Again, just to go over this. If you toss two coins, you can get two heads or two tails. And it is true, you could have one head and one tail. You could say the sample space here, don't write this down because this is misleading. You could say that the sample space here is 3. And a lot of people that haven't taken probability or statistics, they'll say, yeah, there's 3 things can happen. You can get a heads and a tails, or you can get 2 tails and 2 heads. That is technically correct, but it's not very helpful when you're doing probabilities. Why is that?
Yeah, because the weights are different. They're not all equal.
Right. We know, you should know, before the course, that the probability of getting 2 heads in a row, one and then another, if the flips or the tosses are independent, like the coin doesn't remember what it got last time and then try to make up for it. But then there's a joke, if you're a computer science guy in the computer science textbook, when they talk about probability, they say, yes, we know how to make them not independent, the 2 tosses.
Yeah.
How do you make it not independent? Well, they say, well, you make a weird thing. So you're going to toss this coin, right? But it's connected by a bar to the other coin. So this turns around, but this one turns out exactly like that one. So the second one is completely dependent on what happened in the first one.
Mm-hmm.
They say it in the book. I thought that was kind of cool. But anyhow, so what is the issue here? What's the probability of getting 2 heads? Maybe this is too elementary for some people.
2 heads, that's 1/4. 1/4.
Yeah, now this is not such a good. You like, when you're doing calculating probabilities, you like to have equally likely sample spaces. It makes it easy. It's proportional. The probability is proportional to how many cases. You want that. You don't want. So what do we have to do? We've got to go to, just like with the boy and girl thing, we've got to expand this. So the first one being a head and the second one being a tail. In fact, the next part of the chapter talks about equally likely sample spaces, probability, equally likely outcomes. So for tossing two coins, or two dice, what are the possibilities? It goes like this. These are all different. And so forth. So how many outcomes are possible? Well, it's a 6 by 6. So this sample space its size is 36, and they're all equally likely.
What do you call that operator again? The 2 bars?
It's the cardinality of the set.
Oh, yeah. Okay.
Finite sets is just how many elements are in there. So let me see.
Finite set mean again? I'm sorry.
Huh?
Not infinite.
What's that?
Yeah, finite means not infinite. That's all.
Okay.
Yeah. Okay. But what if I give you this? What's the cardinality of the set?
3.
Nope.
Wait, what?
With set notation, it doesn't
Two
matter.
repeated. Yeah.
It's the same thing. It's in there. So it's just been said twice, but it doesn't change what the set is. This is the same as the set with 1 and 2. So it's cardinality too. Just to be aware of the notation.
Oh, okay.
I always test people to see if I've got any gamblers out there, So if I'm looking at a die, right? And suppose that I'm looking, so it's got a three dots, right? Okay, I'm looking down at this die, right? It's got 3 dots. What's on the opposite side? Quick.
I don't remember.
Was it 5?
Yep. Do you play craps?
Nope.
Okay. This is the test. They ask the test to see if I got dice players in there.
Well, what if our dice have more than 6 sides?
We don't. That's if it doesn't involve money, we don't talk about it. So not interested. That's in the classroom. That's in the classroom. But can I ask you a question? Listen, can I leave you with a? Let me ask you a question, okay? I'm measuring something here. It's a common sense sort of thing. An object will tend to land on the heavier side down, okay? So you want, if you're thinking of a die, it's got some holes in it, right? So what now that we know how the faces are, so which side, what would be the most common way for the heaviest side goes down? What would we most commonly see on top if it was rolled?
The 6. Right?
Hold on now. Heaviest side down, right? 6 is got
Heaviest side down. So on top, you would normally have like a 6. On bottom, you would typically have a
no,
1.
but now you've lost 6. You lost some material from the top there to get those right, those holes. So you would think that face would be lighter, right? It would tend to. You see?
Oh yeah, that's what I was saying. You asked which side would face up.
So what's on the other
So I
side?
said probably the 6.
What's on the other side of the 6?
A 1, I believe.
Right. So wouldn't that be a? Oh, I'm sorry. Okay. You're right. I'm having a hard. You guys are having a hard time. That's. I don't know. Maybe it's time for me to retire. But no, you're totally right. So this would be lighter. So if you're playing some kind of game with dice, wouldn't it behoove you to put more money on boxcars or something? Because of that.
Perhaps. I mean, it's
Very
such
good.
a small difference.
Okay, now I got to get my revenge because you guys said no, not revenge, but okay, Aim, I'm going to put you on the spot. How do they manufacture the dice so that we don't have this problem of like one side being lighter than the other?
I don't know. I'm a math major, not an engineer.
It's a common sense
material
thing. It's a common sense. It was in the statistics book. How would this happen? You've seen the dice, right?
They fill it with like paint, right, or whatever.
Well, the problem is if you fill it with paint, that could be a different density.
You heavier paint.
Yes. Well,
for inside the holes.
You guys are closing in on the answer. I'm sorry this is a trivia thing, but that's just the way it is with me. How do I get it to be the exact same density? I don't want to have to measure and be, I want it to be this same density.
You could use the same exact material and just color it differently.
Thank God, you got it. Okay, one last piece of trivia. Let's go back to the heavy side going down. If you spin a penny, okay? Think about that. It's got Monticello. It's got the Jefferson's house on one side. It's got a bust of Lincoln on the other. If you spin that, which side is more likely going to show up? And when it falls over, when it spins and then finally falls over.
Probably whichever one. Like it depends on how the edge is.
Well, I'm getting back to which side's going to be heavier. Which side? Is it pronounced Monticello or Monticello? Or
the head side would be heavier, right?
Which side would be heavier?
The heads.
The heads, right? So you're going to see tails. You're going to see tails there more frequently, and the difference is about 2%. And don't ever get taken. Don't by this, Don't ever get taken by this because that's the one way to extract money from people that think it's a fair game.
That's interesting.
Okay, guys, I kind of BS my way through today. I just what I need to do is reform myself a little bit. No, anyhow, so for on Tuesday I'm going to get more serious about chapter 2, and so what you could do to really help me is to read about the set theory that they talk about there, the basic notations of set theory. Like we're going to look at something called events, which are subsets of the sample space. And so if you have 2 events, you have to know what this means. That's a shorthand for writing this. The intersection of A and B, and this is the Venn diagram that goes with that.
So
but if you read, go ahead.
The test that you're going to post is just going to be chapter 1?
No, it'll be both. But I can post it on the early side because I've given you plenty of time to work on it.
Okay.
I can post it on the early, but I definitely see you can help my lecture. You already helped greatly, by the way, all of you guys. But you can help me for Tuesday by reading this section on events, and it's like a review of set theory there. And it looks simple, but it's not. Okay. And they talk about Venn diagrams, and we'll pick that up on Tuesday. But if you've already had some exposure to it, it'll make me more effective, in what I have to do. I apologize.
Professor?
Yeah, go ahead. Yes.
So, because I know everybody's talking about the test already, so are you, because on the syllabus, I think, unless it's the wrong one,
No,
it
it's not.
says you have it on the 20th,
Oh, really?
unless I'm reading it wrong.
Let me check it, okay? It doesn't say, I don't see that.
Oh, okay. I think I clicked the wrong one because you have two of them.
Oh, I have two posted? I'm sorry. That shouldn't be. It should be the most recent one, you know? I left my old syllabus on there? I'm sorry, did I?
Think you did. Because I'm just looking in the canvas under the files, and then you have one.
Oh, no, it's posted on, no, the real one, the current one is posted on the, it's posted on the announcements. I always put everything on announcements.
Ah, okay.
Yeah, so it's coming up, but it's not right away. But I want to put this exam in your hands so you have plenty of time to work on it.
Okay.
And you said you'll be posting that this week, or
The test, I'd like to, fingers crossed, I'd like to do it this weekend, you know, to try to put it together. I know I've gone really slowly today on the lecture. I apologize for that. But, you know, I just want to make sure I don't lose anybody right away on this.
No, that's fine. That was really interesting about sample space and everything. I think that's.
Well, I hope so. I think I made a couple boo-boos, you know, on the way, but AIM fixed. Fixed. I was heading down the wrong path, you know. So, but what I'm trying to do is warn you about something kind of critical here. It's critical that you practice, look over the set notation stuff, examples they have in the book. Why is this critical? Because there's a super interesting problem, super interesting about circuits. It's at the end of chapter 2. They have these schematics for circuits, and they ask you, with what probability is it complete? You know, the circuit complete. You know, electricity goes from the input to the output, and that requires some skill with using the set notations, okay, and the rules of the distributive law for sets, that kind of stuff. It really requires that, and it's absolutely the best problem in chapter. Hands down, maybe one of the best problems in the book. So just saying that I want you to read closely chapter 2 as much as you can. I don't want you to waste this weekend because it's sooner or later you'll have to absorb that. It's critical to get those notations down and know how to do Venn diagrams. Okay, I think I went way too long here. You guys have been very patient with me today, and I hope it was worth it for you. Well, I'll pick up the pace a little bit on Tuesday.
have a good day,
I
Professor.
really like the explanations. Thank you.
Thank you,
Okay.
Professor.
Professor, just for clarification.
Yes.
So you want to try to post the exam this weekend, but
I would
we'll only
like
be
to.
able to do the stuff from chapter 1.
Well, you could do it.
Technically.
It's not really. I mean, the problems are hard enough, so it takes a while to understand the statement, and regardless if you know the tools you'll need to do it. And I think there's a value in there's some value in just looking at the statement and trying to get down what's being asked here. You know, what's being asked.
But just for clarification for me, so you're going to try to post it, but you know, obviously because we'll have that range of time to do it, like we can do things slowly as we complete the second chapter.
I don't want you to rush. I don't want there to be any pressure. I believe, my own personal belief is that time pressure has no place in math, because some people are really slow, but they're really creative. And you know, we have this wrong impression that those two go together. You're quick and you're smart, you know, and you're creative. And yeah, maybe that applies to Bach. Everything he wrote most of the things he wrote were really good, and he did just tons and tons and tons of stuff. It's unbelievable how much he did. But then there's other composers that didn't do, like Duraflé, more recent. He only has like 4 famous pieces, but they're so good. You know, and so I can imagine him taking a long time to do that. He just wasn't the kind of guy that's going to spit out a lot of a lot of amazing music. I mean, it's just I just don't think rushing needs to be part of learning. I'm sorry. I'm just again, I have all these prejudices. But I don't like in-class tests. I don't like giving them. I don't like grading them. I don't like putting people under pressure. I think the take-home test is a better model. The only problem is that with a class of this size, somebody may receive the test and then immediately go to check, and that's without even trying it, to read the problem, they go to check first, and I think that's just depressing to me, because I try to, the problems I get are I try to make them so that eventually, they're hard, but you get curious about what the answer is, and if somebody supplies you with the answer before you've really gone through your all your moves and your cycles, then I think it's hurting you. This. I still got 17 people. Thank you for hanging. I'm sorry I was late today a little bit.
Well, I agree with you on the take-home tests. I think it's just a better way to evaluate how someone's doing. Just like, if you're going to have to do any math in the real world, you'll have time to do it, and you won't be in a situation where you can't look things up. But of course, that's kind of on you as a professor or a teacher to write a test that would be appropriate for that situation, like where you do have all the time in the world to do the problems. So it's a little harder for the teachers. I get that. And that's what I'm planning on going into. But I agree with you. I think take-home tests are better.
Thank you. Again, there's some traditionalists who say you don't know it unless you can do it quickly. And I don't know about that. Just from music, I realize, there's people that were highly productive, like Liszt, and a lot of his works, piano works, seem to be improvised. It feels like improvisation, like Rachmaninoff, But then there's other people like Brahms who did really polished and took a long time. You can tell all the care and everything's had to be just right. There's different kinds of creative powers, that people have, and I don't think the speed. Yeah, I'm glad you say that, because you're going to be a teacher. I agree, but
well, thank you, Professor. I actually have a class at 2, so okay. I'll see you Tuesday.
Thank you. Have fun.